Hey everybody, this is Mike Bartles from HEC. Within this presentation, I'm going to continue discussing the Clark-Unit hydrograph parameter regression equation analysis for the state of California. This video is part 4 within a series of videos devoted to this analysis. As an overview, within this video I'm going to present how the uncertainty inherent within the regression equations was quantified, and a usage of these regression equations that demonstrates their usefulness. Same as before, I challenge you to name that dam and write it in the comments below. The Clark-Unit hydrograph regression equations represent the most likely T sub c or r value for a given location, as shown by the green star in this figure. However, these equations contain uncertainty which cannot be completely eliminated, and they cannot completely explain the variability in the response. To quantify the amount of uncertainty present when estimating a T sub c or r value for a specific location, prediction intervals can be used. Prediction intervals should be used in lieu of confidence intervals when estimating uncertainty around a yet-to-be-observed data point, since they incorporate both the model parameter uncertainty, for example the error around the population mean at the input value, in addition to the residual uncertainty. When using weighted multiple linear regression, as is the case within this study, the estimation of prediction intervals is complex. As such, statistical software like the R statistical language should be used to estimate the prediction intervals. An example of code that can be used to calculate the prediction intervals around an estimated value is shown here. Uncertainty about any predicted T sub c or r value is assumed to be normally distributed. That's the name of the game when using multiple linear regression techniques. But this is an opportunity to generate a distribution representing uncertainty in the Clark-Unit hydrograph parameters that are predicted when using these equations. The mean and standard deviation of a normal distribution can be inferred from the prediction interval and then sampled within stochastic simulations to estimate the amount of uncertainty in hydrologic model outputs like runoff volume, peak discharge, and peak reservoir elevation when using predicted Clark-Unit hydrograph parameters. Output from just such an example within HCHMS is shown here. First, an R script was used to generate the 5 and 95 prediction intervals. The mean and standard deviation of a normal distribution was then parameterized to represent the prediction intervals. Excel was then used to generate 100 random samples, and parameter value sample objects were created for both T sub c and r. An uncertainty analysis within HMS was then sampled from these input distributions and applied boundary conditions using Monte Carlo procedures for 100 iterations. Time series output at a location of interest was then generated. Within this figure, output hydrographs representing the mean, shown as the solid dark blue line, the mean plus or minus 1 standard deviation, shown as dashed dark blue lines, and minimum and maximum, shown as dashed light blue lines, are shown. An example application of these regression equations for the East Fork Russian River upstream of Coyote Valley Dam is shown here. Terrain data was first downloaded, an HMS project was created, basin elements were delineated, subbasin characteristics were extracted, and then the previously mentioned regression equations were used to predict Clark parameters. The precipitation runoff process was then simulated for a large event. The time necessary to complete this analysis was approximately 1 hour, which is extremely efficient and extremely accurate in generating these results shown here. Thanks for watching this entire series of videos. As an overview of the whole series, I detailed how California DWR DSOD required the development of regression equations that can predict Clark-Unit hydrograph parameters for the entire state of California. We developed 100 HMS models. Regression equations were then developed using calibrated parameters from those HMS models. The regression equations were then validated using 18 additional locations. Uncertainty around the predicted values could be quantified and included within HMS, and how the regression equations can be used to efficiently parameterize HMS models and produce accurate outputs. Now, thank you for watching. Happy modeling, and I'll see you in the next one.